Section 21.1, magnets and magnetic fields. So we're going to take a look at an introduction to magnetism here. The objectives we're going to look at are going to be predict whether magnets will attract or repel in a given scenario, to discuss magnetic field around a permanent magnet, and to discuss the Earth's magnetic field. The first thing to think about are poles, and poles are defined as the ends of magnets, and poles can be labeled as north or south. And the way it works is that the name north or south is really derived from a magnet's behavior on Earth. If allowed to rotate freely, the north end of a magnet rotates and faces the geographic North Pole. So, we have the geographic North Pole and the geographic South Pole. If you had a magnet on the surface of the Earth, the north end of the magnet, and we'll look at a compass here, okay, spinning freely, the north end of it would point toward the North Pole. If you had a compass down here on the south side of the Earth somewhere, say you were standing on the Earth here, okay, it would look like this. The south end of the magnet would point toward the South Pole. Now, this is a little bit counterintuitive because, as you know, like poles repel and opposite poles attract. Okay, and what happens here is the fact that this is really called geographic north and geographic south, and not magnetic north and south. And we'll talk about that difference in a little while. So the second thing to mention again is that like poles repel and opposite poles attract, similar to electric charges. Okay, the only difference though is that magnetic poles cannot be isolated. So electric charges, you could have this positive ion or positive charged point charge in space here when just giving off an electric field. Whereas with a magnet you always have a north and south pole. And we'll talk more about in section 21.2 with magnetic domain theory, where even if you cut a magnet, you still have a north and south pole. A permanent magnet is an object made from a material that creates its own magnetic field. So for example, some materials can be made into permanent magnets by induction, and these materials are called ferromagnetic. Ferro for iron, magnetic. Okay, and this is by magnetic induction. They can be made into permanent magnets. But again, a permanent magnet is an object itself that creates its own magnetic field. Now, all materials respond to magnetic fields, but some more than others, depending. Now, what we'll say is that a magnetically soft material has a tendency to be easily magnetized, but it doesn't hold this magnetism. So a material that is soft, you can make it into a magnet very easily with a weak magnetic field, but it won't hold that magnetism or a short period of time, but it won't remain a permanent magnet. It won't stay magnetic. Whereas a material that's magnetically hard is difficult to magnetize, but it retains its magnetism. It's very similar, magnetically hard was the other one, very similar to specific heat capacity with thermal energy. Something with a high specific heat capacity takes a lot of heat to heat it up, like a baked potato. You have to leave it in the oven for hours, for hour and a half or so. But when you take it out, it stays hot for a long time. That would be like a magnetically hard object. Whereas something like water is considered to be magnetically soft. You can heat up water pretty quickly, but it'll cool down pretty quickly. And finally, a magnetic field is a region in which a magnetic force can be felt. And traditionally, the direction of the magnetic field at any location is simply defined as the direction which the North Pole of a compass would point at that location. Now, think about this logically. The North Poles are all of these colored in poles here, right? These are all the North Poles. And what you notice is that the North Pole faces away from the North Pole of the magnet because opposites repel. So this North Pole here is going to want to feel the south part of the magnet or the compass pulling it toward it. Whereas here, the south part of the magnet pulls the North Pole of the compass toward it. And at any point along the way, we'll see that the North Pole points in the direction of the magnetic field. North Pole pointing in the direction of the magnetic field. On Earth, the North Needle points to that geographic North Pole, which is what we talked about earlier, but that's really called magnetic south. And that's one of those things about the Earth that's weird. This is the geographic North Pole that's labeled there. This is the geographic South Pole, but this is really known as magnetic south, and this is really known as magnetic north. Okay, so if you think about it, it's kind of switched. And it makes sense because, well, we said that the North Pole of a compass points toward the geographic North Pole. Well, that doesn't make much sense in this sense, because if this is a North Pole, it wouldn't point toward a North Pole, it would point toward a South. Well, magnetically speaking, this is South, this is North, so opposites are attracting, even though we call this geographic North. The next thing is that the Earth's magnetic field, its source is not really iron. Now, it's more likely to be due to the movement of the charges in the convective currents in the Earth's core. We don't really know for sure, it's still theorized, but we know that there are convective currents of the fluids that are flowing in the Earth's core, and that is theorized to be the likeliness of the reason for the Earth's magnetic poles. Next is that the strength of a magnetic field on a planet is thought to be directly related to its rotational rate. So if we have like the Earth here spinning on its axis versus another planet of the exact same size that is spinning much greater, the magnetic field caused by the planet spinning much faster will be greater than the one spinning slower. And then finally, another interesting fact is that on Earth, a lot of bacteria actually have internal magnetic structures, and they use the Earth's magnetic poles to know where they are moving. So if a certain bacteria needs to come to the surface versus staying under the water, it knows which way to move based on the polarity of the Earth, because its internal structure is magnetic itself, so it can sense that push or pull.